Hello and welcome back to our next maths lesson. So today we're going to be using the skills that we've gained in equivalent fractions and our understanding of fractions in order in sequences in order to think about ordering and comparing fractions. But we're going to start within one. So we're not going to think about mixed numbers at the moment or improper fractions. It's all going to be the fractions between 0 and 1. And it's going to be mainly focusing on the skill that we've got of equivalent fractions and how we can use that to help us. Now, there are some rules that really help us think about an easy, quick way to answer a comparison problem with fractions. There are 3 rules in total that we can use to help us. And each of these rules are a shortcut in a way, but use the knowledge of fractions to help us come up with an answer. So before we do that, we're going to answer these questions here. One is a quick recap of equivalent fractions, and the other 2 are knowledge that we've used when we looked at multiplication and division. Have a go for me. Pause now and give it a shot. Okay, so the first one is a complete the equivalent fractions. So the first thing we notice is we need to know what we've done. Now we've got both of the denominators, the bottom number. So we see what the relationship between them is. And the relationship is timesing by 4, which, according to our rule with equivalent fractions, we must do the same to the top as we do to the bottom. As we times the bottom by 4, we must times the top by 4. So we times the top by 4 and we get 8. So 2/5 is the same as 8/20. Next one, it says write down the first 7 multiples of 7. So all you need to do is use your multiples and write them down in your times table order, and that's it. The same with your 4 times table. Then it says what's the lowest common multiple of 4 and 7. So what you're doing is looking along each of these lines to see which of them is the same. So we go along here, what's the first number in both of these two? Well, it's 28. That's the lowest possible one, which is the same. So our lowest common multiple is 28. There is a trick here that you can look at, which is what 4 times 7 is, which is 28. But that's not always the case. But it is a very good use of a way of comparing fractions if we know we can just times 2 together to get a common multiple. So, writing greater than or less than or equal to, compare the fractions we have here. We've got 3/10 and 7/10. So we can draw a diagram to show it. On the first one, we've got the 3/10, and on our second one, we've got 7/10. Quite obviously here that 7/10 is the largest out of both of them. So 3/10 is smaller than 7/10, or 7/10 is larger than 3/10, no matter which way you go about it. So you could draw a diagram here. Now this links into the fact that if we know the denominators are the same, we can start to make a rule up. And the rule is when the denominators are the same, the greater the numerator, the greater the fraction, or the smaller the numerator, the smaller the fraction. So if our denominators are the same, we can just compare the numerators as we normally would. The bigger it is, the bigger the fraction. And that's our rule. So using that rule, how can we help us answer this one? Well, we know our rule is smaller than or greater than and greater than. So if the denominators are the same, we use it. But our denominators aren't the same. What piece of knowledge do we have that could allow us to make the denominators the same? Yes, you guessed it. It's equivalent fractions. So we know that we can think about the multiples of 5 because we can times 5 by something to get to 15 because we want to compare the same denominator. So 5 to 15 is here, and we have to times by 3. So we times the top by 3 as well, which is 6. So 6/15 is the same as 2/5. So we can say 6/15. Now we've got the same denominator. We can compare the numerators. 7 is greater than, so 7/15 is greater than 6/15. Because 6/15 and 2/5 are the same, which is what this tells us, then this one means it's the same way as this. And that's all because of equivalent fractions. We are just finding a fraction which is the same as each other. And that means then we can compare fractions with the same denominator and know that this one would be the same as this one. So, pause now and have a think at these ones for me. Okay, so first off, we have to look at the relationship between 6 and 18. That's timesing by 3. So I times the bottom by 3 here. That means I have to times the top by 3 as well in order to keep it equivalent fractions. These two are the same here. So 3/18 we can now compare with 5/18, which means that 5/18 is bigger. We look down here at these two. We always go to this one. We could come down if we wanted to, but it's much easier to go up to the larger denominator if this is a multiple. So 5 times 5 is 25. So we have to times the top by 5 as well. Now we have the same denominator. We can compare them. 15 is larger than 12. So 3/5 is larger than 12/25. Now we've got 36 and 9/9. Well, trick question. Both of these are equal to 1, so they're the same. We didn't even need to look at equivalent fractions because we know that if we have the same number on the top as we do on the bottom, it's equal to 1 whole. Both of these are equal to 1 whole, which means they are the same. They are equivalent fractions indeed, in fact. So, have a think about this one. I know that 4/7 is greater than 5/11 without having to draw a bar model or having to find a common denominator. How do I know? Okay, so this is using another piece of information that all of us are pretty good at, which is halving. So how does this minion know that 4/7 is greater than 5/11? Well, they know that 7 divided by 2 is 3.5 or 3.5. They know that 11 divided by 2 is 5.5. So what you're saying is this 4 here is bigger than 3.5. So this entire fraction is larger than a half. Whereas this one, this number is smaller than 5.5. So 5/11 is smaller than a half. If this one is larger than a half and this one's smaller than a half, then this one must be bigger than this one. So 4/7 must be bigger than 5/11 because we are comparing them to a half each. One is smaller and one is greater than. We know that when we compare the two of them together, they're the same. It's the same way as if I was to say, okay, I know that 5 is greater than 4, and I know that 3 is less than 4, so I know 3 must be less than 5. That's the same idea. So have a think about this one. Could you use your knowledge of halving in order to help you? Okay, so let's think about it. We know that half of 14 is 7. Okay, so 8 is larger than 7. So this one is greater than a half. Yeah. Then we also know that half of 22 is 11. 10 is less than 11, so it's less than a half. So the one that is bigger is at the 8/14. See if you can use it for these ones here. Doesn't quite work the same. So we need another rule. Now, this is interesting because we've got the same numerator in both of these two, but different denominators. So we could draw a bar model to show it. Here's 4/9 and here's 4/5. Here's 2/3 and here's 2/7. Have a think. What's the same and what's different? Is there a pattern? Well, there is a pattern. So we know that 4/5 is greater because on our bar model it quite easily shows that, and our 2/3 is greater, and that because it shows it on our bar model. In both cases, we're looking at the one, if their numerators are same, the smaller denominator actually is the bigger number or the bigger fraction. And that is actually our rule. When the numerators are the same, the greater the denominator, the smaller the fraction. So 4/9 is smaller than 4/5 because the denominator is bigger. And the reason for this is that you're cutting a whole into smaller pieces. And even if you have the same number of pieces, you've got smaller pieces than the other person who's got larger pieces. So, of course, you'd want the bigger pieces. And the same number of bigger pieces as the other person still means you've got more because your pieces are bigger. And that's what you're saying. It's a little bit odd. This is a little bit of an interesting rule, but it works perfectly. When your denominators are the same, the greater the denominator, so the bigger the number on the bottom is, actually the smaller the fraction is. Vice versa, the smaller the denominator, the greater the fraction. If I'm only having to cut my cake into 2 pieces, I have a massive piece, but if I'm cutting it into 10 pieces and I'm having 1, I've got a tiny piece. So using that rule, can you answer this question? 1/3 is greater than or less than 1/100th. Well, it's greater than, because it follows the rule of the denominator being smaller, the greater the fraction. Or 1/100th has a really large denominator, so it's a very small fraction. So compare these fractions, 3/7 to 6/11. Now, we can use our numerator rule and get the numerators to be the same, because 7 and 11 don't go well together. So I can't get my denominators being the same. But 3 and 6, now they do go together well, because 3 times 2 is 6. So I could get the numerators being the same. I could times that by 2 to get 6/14. Remember, I have to do the same to the top and the bottom, so I times both numbers by 2 to get 6/14. Now I have 6/14 and 6/11. The denominator is the same, so I can look at which of the denominators is smaller and know that's the bigger number, or I can look at whichever denominator is the greater and know it's the smaller. In this case, this denominator is larger than this one, so this one is the smaller one. So it will go that way, which just means it sits up here. Have a think about these ones. Give it a shot. Use that rule we just tried. If you need to, go back, have a look at it again. But try and make it so the numerators are the same, then compare denominators. And think, as long as I do the same to the top and the bottom, the fractions will be equivalent. They will be the same. Pause now and have a go. Okay. So 3/10. 3 goes into 12 4 times. So times it by 4, that's 12/40. 40 is larger than 37, so it's smaller. 20 can be halved to make 10. 10 31s and 10 27s. 31 is bigger than 27, so 10 27s is bigger. And 5, I can times it by 3. 1 to 3 is times in by 3. That's 3/15. 15 is larger than 8, so the 8ths are bigger. Pause now and have a go at your answers for me. Okay, so the answers for our questions. First off, we are able to use the bar models to draw. So we do 7/8, colour them in, 3/4, colour it in. You can know which ones are bigger because it's got the bigger amount. These two are equal as long as we colour them in correctly. And this one, 2/3 is larger than 7/12 because of our bar models. Over here, you can see that there's a relationship between the denominators. So what you're doing is changing using equivalent fractions to change them. So 1/15, 5 times 3 is 15. So 1 times 3 is 3. 3 is smaller than 4. Times it by 3 again, that's 6. So 6 is bigger than 4. 2 times 3 again, because it's 5 to 15, makes 6. They're the same. 3 to 15 is timesing by 5. So I times the top number 5 is 10, so bigger than 6. 3 to 12 is timesing by 4. So 2 times by 4 is 8, so the same. 3 to 9 is timesing by 3. 2 times 3 is 6. 6 is the same, so the same. Over on this side, we can do the same way. 3 to 9 is timesing by 3, and it doesn't matter which way round I do it. That's timesing by 3, so times that by 3. 3 is bigger than 2. 3, that's timesing by 3, so I times this by 3, and 3. 4 is bigger. 3 times 4, so 1 times 4 is 4, they're the same. 3, that's timesing by 4. 2 times 4 is 8, they're the same. 3 times 4 is 12, so 3 times 4 is 12. This is 1. Actually, we didn't need to work it out. This is 1. Makes it nice and easy. Bigger than this. 4 times by 3 is 12. 3 times by 3 is 9. And 9 is bigger than 8. That's how I would work it out. Then we sort the fractions into circles. So greater than a third, equal to a third, or less than a third. And we've got all of the ones in here. Using the same rules, you can do it that way. And these are your answers. Thank you for listening, and I will see you in the next video. Actually, before we go, I've just noticed that number 4 hasn't been answered. So let's have a look and see if we can go through it. What could be the missing numerators and denominators be? Write a number in each box to make the statements correct. So 5 to 15, the relationship is timesing by 3. So 5 needs to be greater than whatever I'm timesing by 3 up here. So 2 would make it 6, which wouldn't work. So 1 does work. This is timesing by 2. I need 5 to be bigger, so I could do a 1 or a 2. It wouldn't matter which. 2 times 2 is 4, so that would still work. 12 times 2, or 6 times 2 is 12, or 6 divided by 2 is 12. So if I'm dividing by 2, I need 5 to be bigger, so I could have this at 4 twelfths. 4 divided by 2 is 2. That's smaller than 5. So we're all good. Over here, we know our relationship to go from 3 to 6 is timesing by 2. We've got 5 of them, and that's greater. So anything times by 2, which is less than 5, we could use. Our relationship here is interesting. We haven't got one, but what we're looking at is the relationship down here. So if I was using 5 and I times it by 3 to get 15 here, I'd have to also times that by 3 to get 9. That wouldn't work. No, because this needs to be bigger. So if I times it by 2, that would put 10 here. 5 tenths is not, times this by 2 is 6 tenths. Wouldn't work. So we might have to draw this one out because this is less than this. 5. The other thing that we could do is make it so we compare it in a different way, or it could be anything we like. So 5/5, timesing it by 1. 3 is less than 5. Nice and straightforward. Here we've got the denominator. Our numerators are the same. So as long as our denominator, in order for it to be bigger, our denominator is less than 6. So any number less than 6 would work. It would make it an improper fraction, but it would work. So we can compare them. We could even put 5 in here and have 5/5. That's 1. That's still bigger than that. What do we need to make it? To be fair, there is so much we could do. If we just made it 5/5, it's still 1, which is bigger than this. We could put 5/5. There's still 1. This is straight bigger than this. This could be 5/5. There's still 1. This is still bigger than this. So a nice easy trick at the end there. Thank you, and I'll see you in the next video. Goodbye.